Okay, all right. Well, hello and I guess good afternoon. It's week 2. It's only been 2 weeks, but I have to start talking about our midterm exam, which is 1 week. What's that?
The screen, sorry.
The screen. It's yellow.
Oh, it's yellow.
Yeah. It's weird. I don't know what's going on. I think something's just wrong with the projector. I gave them a call and they said they'll look into it. But we can still read it a little bit. It's not great, but we can still read it. Okay. All right. So midterm exam. 1 week from today, it'll be here in class. And pen and paper, or I guess pencil and paper. It'll be a paper exam. Okay. You'll need to bring a calculator, and I've provided a document that covers topics that will be on the midterm exam. Okay. So anyway, exam will be an hour and 50 minutes long. If you're sick, don't come to class. Okay, just send me a message and we'll figure out some makeup. Okay. And then yes, this file, don't share it, okay? But what do I have written here? Okay, so you will be allowed to have 1 sheet of notes, okay? So 1 letter size sheet of notes, writing on the front and back. You can do typing as well, or shrink down little problems and whatnot. And then and I'll collect those at the end. I'm also going to send out a seating chart, okay? So before the exam, I'll send out some info, like this is where you're going to sit, and that's where you will sit, okay? If you're watching on the video, you got to come in person, okay? So I know there's a lot of people enrolled, and maybe a third or a quarter of students actually physically come to class. So everybody else who's watching video, you do need to attend in person for the day of the exam. Okay, these are the topics that will be covered. I think it will make sense. So you'll have some vector-based gradients. So I'll give you a function in vector notation, and I will ask you to calculate the gradient of this function with respect to a particular vector. So in the notes, there's doing finding the gradient of the OLS loss function with respect to W. In your homework, you did find the gradient of the weighted least squares loss function, and you can kind of think of other possible gradients that you might need to calculate. And I might also throw in, it's not listed here, but maybe I'll ask you to set that gradient equal to 0 and solve for W as well, okay? So be prepared to handle those kinds of operations there, okay? Another function or another problem you might have is a gradient descent problem. So I'll provide some kind of function in 2 dimensions. I'll provide some kind of arbitrary starting point and an arbitrary learning rate. And I will ask you, okay, if this is your starting point, this is your learning rate, what is the value you're going to have at the next iteration? So you'll kind of just manually perform the gradient descent algorithm by hand. So you'll definitely want the calculator for this, and that will involve calculating the gradient, or at least the partial derivatives with respect to each component, and then you'll plug your values in and you'll kind of carry this out. So you'll have to demonstrate that you are able to kind of conduct gradient descent in a manual form. I'll also have some questions about kind of the regularized loss functions. So I'll provide a very small data set, maybe 3 or 4 data points, and I will also provide a current line of fit with it'll say this is the slope and this is the coefficient W0, W1, W2, or whatever, and I'll ask you, okay, what is the OLS loss? So if OLS loss it could be like sum of squared errors or mean squared error. You'll calculate the residuals, square them, add them up, divide by n maybe. Okay, and then I'll ask you, okay, what is the lasso loss? All right, so if you include the penalty term for the model complexity according to lasso, the L1 penalty term, that will adjust what the loss function is. I'll ask you to calculate the ridge loss, okay, the value of the loss function for ridge regression. So you'll have to, figure out what the penalty term there and things like that. And again, when you're calculating these LAS or ridge regression penalties, don't include the intercept term. Okay. You'll also have a leave one out cross-validation problem, okay, and you will do this kind of manually. So, I had an example where we fit a linear regression line, and I said, okay, if we leave this point out and you bring it back in, what's the error there? So for this, I'm going to provide another small data set, maybe 3 points or 4 points, and there will be kind of two different models here, okay? And you'll perform leave one out cross-validation for each of the models. And so I'll say, all right, if these are your 4 data points and you leave point number 1 out, this is what the line would be if you fit it to the other 3 points. So I will provide the equation of the lines when you leave that 1 point out. You don't have to, do linear regression or something to figure out what that line is. So I will provide the equation for the lines when you fit it to n-1 points. But given that line, you'll have to figure out what the prediction is and what your residual would be for that for your test case. Okay. There will also be a numeric gradient calculation for a neural network. So today I'll we'll do a little bit more on regularization, and then we'll introduce neural networks today, and then on Monday's lecture, we'll cover some neural network stuff. And so, we'll talk about calculating gradients for the neural network. And number 5 is, really being able to do a numeric gradient calculation. So we've already covered how to do a numeric gradient, and that's where you add like a small value, like h equal to 0.01 or something like that. And you say, okay, if I add it to this component, how much does my loss function change? All right, and that will give you one component of your gradient. If I add it to the other component, if I add 0.01 to the function, how much does the loss function change? Divide by the size of h, and that will also give you an estimate of the gradient. So here it's the same idea of doing a numeric gradient calculation, except the gradient here will be for a neural network, okay? Or the loss function will be for a neural network. And so we'll introduce that. And then I'll have a handful of conceptual questions. Some of these conceptual questions will be taken directly from the notes, and some will require you to do a little bit of thinking. It will be like a question where the answer is not explicitly stated in the notes, but you'll have to kind of do a little bit of thinking and piece together, all right, what are the implications of this property or something like that. So a little bit of conceptual thinking there. Okay, and that should take about an hour and 50 minutes to complete, which, that's the design. The design, when I try to write an exam, I try to ballpark how long it will take. And, as I've taught this class multiple times now, I think this is about the right length. So, in the beginning, I either make the mistake of writing the exam too long or too short, and then I make adjustments accordingly. And now I think the length is appropriate, I hope. Well, we'll see. Okay. So that's next Wednesday. I know, it's like summer session is fast. It's we have to discuss that. Okay. Well, anyway, let's talk a little bit more about regularization and the bias variance trade-off, and then we'll also eventually get to introducing neural networks. So, with the thing about these summer session lectures, it's kind of like I'm piecing together, multiple lectures into one. So if it seems like there's a huge jump in topics, that's because during the regular school year, they are two separate topics. But yeah, we got to kind of compress everything here. I still hope you're enjoying the course and feel like you're learning stuff. And so let's talk about what regularization is. Okay, so remember regularization. What that does is it takes your loss function. So you might have, we start off with something like the ordinary least squares loss function, where we say we want to minimize the squares of the residuals. We want to minimize the mean squared error. And what regularization does is it says, okay, we'll take the OLS loss function and we will combine it with a what? What kind of term? A penalty term, right? We add a penalty term for how complex the model is. So we take the OLS loss function, we combine it with a penalty term that says, okay, if it's really complex, we're going to punish the model, okay? And we have this blank term that says which of these things is more important. Is it more important to minimize the OLS? Of course, that's going to be important. Or is it really, or how important is it to minimize the penalty? And so that is our lambda term, okay? All right, so we combine it with a penalty for complexity, and then the lambda term is used to determine, which of these goals are more important. Okay, so we introduced lasso and ridge regression. And both of these we're saying, okay, L represents the mean squared error, basically the loss function for ordinary least squares regression, and then we have lambda times complexity. For lasso, this complexity is the sum of the absolute values in our coefficients, right? So if your weight coefficients W are big, you have a bigger penalty, and we're looking at the absolute values. Ridge regression takes the squared coefficients, and so if you have really big squared coefficients, then ridge regression penalizes it. And so these regularization techniques these are also called shrinkage methods. Shrinkage because they have the effect of shrinking the W coefficients, right? So lasso says the penalty is if your W is too big. So when you introduce this complexity penalty, the tendency is for the model to reduce the size of your W coefficients. Okay, and in some cases it reduces them down to 0. Okay. We have ElasticNet. ElasticNet, you can kind of think of this as a hybrid between lasso and ridge regression. So it says, okay, for the complexity parameter, right? So lasso, we use the L1 norm, and then ridge regression, we use the L2 norm, okay? And what ElasticNet does is just, it's a name. It's kind of a hybrid between these penalties, and it says, you know what, we are going to add both the L1 norm and the L2 norm. Okay, so we're going to add both of these things. And these things get multiplied by some term alpha, okay? And so, so you still have this lambda, which says how much of the penalty is applied, but then this parameter alpha determines kind of the balance between L1 and L2. If alpha were equal to 0, okay, then there's basically no lasso, and it's entirely ridge regression. If alpha is equal to 1, then it's entirely lasso and no ridge regression penalty. And if it's like alpha equal to 0.5, then your penalty is half lasso and half ridge regression. So it's kind of this, now you have this knob where on one side you have circles as kind of your penalty contour, and on the other side, if you turn the knob the other way, you end up getting diamonds, okay? And you can kind of imagine, I don't know, some kind of slider on an app where like on one side you get the circles, and as you slide it to the other side, they turn into diamonds and things like that, right? And then you have like another slider that just says like how much penalty are you applying? And then, on one extreme, you have no penalty, so you have entirely OLS. And as you kind of slide it the other way, you get, whatever penalty you have with the elastic net. Okay, so now you have these two parameters to kind of mess around with, and this has all been kind of implemented in this package GLMnet. Okay, so this I've taken directly from the documentation for this package GLMnet. Okay, and it says it is known that the ridge penalty shrinks the coefficients of correlated predictors towards each other. All right, and we saw that, right? On Monday's lecture, I showed you like there's that line where W1 is equal to W2, where the coefficients for your X1 term and your coefficient for your X2 term, we had that dotted line that said these things are equal to each other, and ridge regression tends to kind of push the values towards that line W1, W2, and then starts to shrink them towards 0. I don't know if you remember that illustration from Monday, okay? And then lasso, what that will do is it shrinks the values of your kind of W1 and W2. It shrinks them towards 0, and so it ends up kind of, one of those gets shrunk to 0 first, and it says lasso tends to kind of pick one of these coefficients, or basically one gets left and the others are discarded. And here it says elastic net penalty kind of mixes the two. If you have a bunch of predictors and they're kind of correlated in groups, then an alpha of 0.5 tends to select like the groups in or out together. So it might kind of say, okay, these are kind of correlated, and kind of we're going to group this together. All right, this is a high level parameter, and users can kind of pick a value up front, or you can kind of trial and error and try out different values. That's kind of a little bit of a theme of machine learning, is a lot of this is trial and error. I saw in CampusWire there was a question about, how do we, when we pick a starting location for gradient descent, is it just random? And the answer is, I wouldn't say it's random. It's a little bit arbitrary, but if you have an idea where the optimal value would be, obviously you kind of want to start closer to it. But sometimes you have no idea where to start, and so one strategy is to start off at a random location, but then run the algorithm multiple times. So you will start off at different random locations. So, imagine, kind of being on some surface and you have like this ball, and gradient descent is basically just letting the ball roll downhill. And so you start in one location and you let go of the ball and it rolls downhill and it settles somewhere at like a local minimum. Okay, and you start somewhere else and you let the ball roll downhill. Now, if the contour, the loss function is just this big bowl, all of them will just roll towards the bottom, the global minimum there. Okay, but if you have kind of this weird surface that has different local minimums, different starting locations could end up at different local minimums, and gradient descent is not guaranteed to end at the global minimum, and it's not even guaranteed to converge at a local minimum, as we saw. If your gamma was too big, it like wiggles off and it shoots around. So things like that could happen. So a strategy is like pick out several different starting locations, allow the gradient descent algorithm to run, and what you're hoping for is that like multiple of these starting locations kind of arrive at a similar minimum, which is kind of like the minimum of all the values that you've arrived at, and you go, okay, well, now I'm feeling pretty good that this is going to be the minimum, and this is a good solution to our thing. Okay. Okay, so here I'm going to just demonstrate how to, if you wanted to try out GLMnet using the package, it would look kind of like this, and this is fine. I do want to kind of just throw an aside. and say, if you're like in 101C, where I'm teaching like model fitting and I don't know, statistical models and stuff, and I'm doing this very kind of practical approach of like, how do you, train a model based on, some particular strategy here. GLMNet is one of the things you can do, and in that class I'm using Tidy Models, and it's implemented in Tidy Models, and you can create a parsnip model for that. So that this goes to like the 5 students who are enrolled both in this class and 101C. You would probably not use GLMNet directly. In that class I would say use the Tidy Models package, where they've kind of set up an interface to interact with GLMNet. But anyway, let's talk about if you wanted to use GLMNet directly, how would it go? And so one thing is that the usage of GLMNet is very different, or in my opinion, pretty different from using, say, LM. Okay, so I think a lot of you are familiar with using LM, where you say, I want a linear model where y, we're predicting y tilde based on, x1 plus x2 plus x3 or something like that, right? And you list off kind of your variables, and you write this formula, y tilde, and you put the variable names. And that's kind of R's interface for creating models. If any of you have used Python and scikit-learn, okay, in scikit-learn, the way you specify a model is you say, these are my target values. This is my y matrix, or vector of y values. I guess it's my array, my NumPy array of y values. And then I also have a matrix X, and all of the predictors are in different columns in this matrix X. And then you say, fit the model according to this in scikit-learn. And GLMNet kind of takes that scikit-learn approach, where it says, don't give me a formula, y tilde x1 plus x2 plus x3, but instead put all of your target values in a vector y, and put all of your predictors into a matrix X. And so that's what this looks like. So we're going to say we have all of our predictors in this matrix X. So X might have n rows and 5 predictors or something like that. Okay, 5 columns. And then our target values that we're trying to predict are in this vector y. And then the default is for alpha equal to 1. So remember, alpha equal to 1 corresponds to lasso and no ridge regression penalty. And so this would kind of fit a lasso. And so this, the result is we get this fit model there. And we'll see. Okay, so I'm going to just demonstrate what GLMNet would look like on this toy data set where I've got 4 predictor variables. Before I do that, let me give you your first view quiz answer for today. The first view quiz answer today is the letter D. D as in dog. D as in dog. Okay, so what we're going to do is we're going to just generate some artificial data. And I've got 4 variables, and there is correlation between these variables. X1 and X2 are correlated, X3 and X4 are correlated, okay? X1 is independent of X3 and X4, X2 is independent of X3 and X4, and vice versa, okay? And the true values of Y are going to be, the true relationship is that we're taking our x1 values and we multiply it by 3, and we take our x3 values and we multiply it by 1.8. And I apologize if it's hard to read on this screen here, but there is a true relationship. The true relationship between x and y is that only x1 and x3 are related to y, okay? But again, x2 is correlated to x1. So if you look at, is there a relationship between y and x2, there's going to appear to be a relationship. Okay, x3 and x4 are correlated, and so if you just say, hey, is there a relationship between x3 and x4 and y, it will also look like there's a relationship. We're also adding some random noise to get what the actual y values are. So the observed y values is basically this true relationship which depends on x1 and x3, plus there's random noise, which is just going to kind of make it a little bit trickier. And so we want to see, like, can this pick it out? So just keep in mind the true coefficients should be 3 for x1, 0 for x2, 1.8 for x3, and 0 for x4. So can we remember that? 3 and 1.8 for x1, x3, 0s for x2 and x4. Those are the true relationships. So here I'm going to try out lasso. I'm going to say fit our y values based on the x predictors here. And when you ask what is the result of this, you get this mess that's like hard to read. Okay, this is very different from, you know, when we fit a LM, linear model, it comes out and says, here's your intercept and here's your, you know, these are your coefficients. And here we get this weird chart that says df 0, 1, 1, 1, 2, 2, 2, 2, 2, and then percent dev 0, 10.9, 20.12, 27.7, lambda 3, 2, 2, 2, you know, all kinds of weird stuff. And it's hard to interpret and understand what's going on here. Okay. So what we're getting is basically a listing of 3 columns. The first column is how many additional degrees of freedom this model spends versus the empty model. So the empty model, in linear regression, what is the empty model? So in linear regression, if you had basically no x predictors, that's your empty model. Basically, you have no predictors in your, as far as the model goes, okay? But you still end up using 1 degree of freedom there. And what is that? That corresponds to calculating the intercept. Okay, sure. What would the intercept be, though? What's that? Well, it ends up being the mean of your y values, right? So if you had no predictor variables, right? So if I said, like, I don't know, a stupid thing, we're going to say, let's predict someone's weight based on their height, okay? Here, our predictor is someone's height, and basically we're going to say, if you're taller, we expect you to weigh more. If you're shorter, we expect you to weigh less, and we'd have some kind of coefficient in there, okay? That would be a model where you have 1 predictor. If we took away that predictor, height, okay, and we just say predict someone's weight, I'm not going to tell you anything about this person. You have no idea how tall this person is, what their gender is, whatever their age is, or whatever. You know nothing about this person. What should you predict? And the answer is going to be the mean, right? If your goal is to minimize the sum of squared residuals, the safest guess is to just predict the mean. So that you end up using 1 degree of freedom in the empty model just to kind of calculate that mean, okay? And then we say, okay, well, if we want to estimate, include a predictor like the height, now we have another term to estimate, and that uses up an additional degree of freedom. And basically, every term you add to the model uses up an additional degree of freedom, okay? So that this first column just says, okay, basically this first row corresponds to the empty model. 0 degrees of freedom, okay, are used compared to the empty model, okay? And then this is, we've got 1 predictor, basically 1 additional degree of freedom is used. And then here when we get df is 2, we're having 2 predictors. We get 2 additional degrees of freedom. So degrees of freedom in this column is basically how many predictor variables are being used in the model, okay? The middle column is the percent of the deviation explained. This is pretty much your model's R-squared value, okay? So R-squared is basically, you know, if you calculate what is the sum of squared residuals, that's basically like your variance, right? Variance is effectively squared distance from the mean, and you're taking the, I guess, the average of that. Variance is your mean squared errors, basically. And so if you are predicting only the mean, you haven't done a better job of just using the mean. And so your R-squared value there is 0, and that's what this is. And as you increase your predictors and as you also increase the size of your coefficients, you are going to improve your model's R-squared. And so what we're seeing is this starts off at 0 and starts to climb up to like 0.93, and we're getting like an R-squared of 0.93, okay? And then the last column is the value of the lambda term used by GLMNet. Lambda is basically how much of a penalty is applied for complexity. So when lambda is big, that means the complexity is punished greatly. So when we have a big lambda like 3, any model that has a coefficient is kind of punished heavily, and that's why it favors a model with basically no coefficients. So large lambdas push the coefficients down to 0, whereas small lambdas say we are not going to punish the complexity as heavily. Go ahead and let your coefficients get big, and because again, for lasso, we measure complexity by how big our coefficients are. And so a small lambda corresponds to large values, or larger coefficients, okay? And if lambda reaches 0, then there's no penalty for complexity, and your solution is equivalent to the ordinary least squares solution, okay? Just for comparison, the R-squared value for OLS, this is a typo here, I don't know what that is 0.954, okay? The R-squared value for, I have no idea where that number came from, something else, okay. The R-squared value here, if we look at multiple R-squared, is 0.954, so that is the OLS, and we can see LM did a good job of picking out what the estimates are. It got a coefficient of 3.04 and a coefficient of negative 1.84, and said those ones are significant, and it recognized that x2 and x4 are not significant. So it did a good job there, okay? But it still has the, tiny coefficient of negative 0.01 and 0.05. If you say, hey, I want all 4 terms in here, OLS says, okay, these are the coefficients there, okay? This is what the R-squared values look like as we increase our lambdas. So we start off at around 0.954. As that lambda grows, our R-squared value decreases, okay? And then it decreases further until we're not able to explain any of the deviation, okay? So you might wonder, like, why would I want any kind of, like, why wouldn't I want 0.954 for my R-squared, right? Why would I ever pick a lambda of like 1.5 or something? Like, why not just pick lambda equal to 0, okay? And the answer is yeah, you'd probably want a pretty small lambda in this case that's going to get decent model performance, okay? But again, one thing to note is these are the estimates that I have for x1, x2, x3, and x4. With lambda equal to 0, these would be the coefficients. And so I'm getting a coefficient for x2 and a coefficient for x4. These are not significant, but I'm still getting some kind of coefficient estimate. And so one thing that Lasso does is if we apply a small penalty for complexity, it will probably have the effect of zeroing out the x2 and x4. It will probably push those coefficients down to 0. It will also have the effect of shrinking this coefficient, so maybe from 3.04, maybe down to 2.9, and maybe from negative 1.8 to maybe negative 1.7. It will have the effect of kind of shrinking these coefficients, okay? But it will also shrink the coefficient for x2 and x4 down to 0. And remember, this is based off of just one random data set. And so if I were to collect another random data set, okay, we would have different noise. And if I were to fit ordinary least squares regression, I'll probably get similar coefficients. But again, this coefficient for x2 will probably not be exactly 0, and the coefficient for x4 will probably not be exactly 0. But with Lasso, I would say the coefficients for x2 and x4 will probably be 0 in both of those cases, okay? And so, so that's what would happen in Lasso. Remember, with machine learning, the focus is we are relieving the human from making decisions and putting a lot of this decision making onto the algorithm or the machine or the steps or the process here. And so as a human, you would look at this summary table and you would say, oh, this thing is not significant, this thing is not significant, so I'm going to remove these variables from my model and I'm going to just include x1 and x3. But you have to make that decision as kind of a human, right? And you might implement some kind of stepwise variable selection algorithm or something like that, okay? Lasso is just kind of like, I don't want to do any thinking. I want you to just go ahead and zero out variables that aren't important, right? And so if you implement lasso, it's going to just zero out the x2 and the x4. It's also going to have the effect of shrinking x1 and x3, but that's a little bit of the cost or the side effect of not having the human make decisions, but just letting the kind of algorithm or the machine do the learning for you, okay? Pros and cons. So you can take a look at the coefficients that would get estimated, all right? And so if it starts off, here I have, you have these dots. This is what is called a sparse matrix. If it's a 0, it just puts in a dot, okay? And as, and so in the beginning, it just has one term, and as we allow for a smaller lambda and more degrees of freedom, it now has 2 terms. Okay, if you don't like having dots here for the sparse matrix, you can call as.matrix and it will fill in the zeros for you. So these are the exact same values, 0.2736845, but rather than dots, it puts 0.00, 0.00. So I don't know which of these things are preferable as far as reading the chart there. That's what you have. And you can see as you reduce the lambda penalty to something smaller, these values, these coefficients get really close to the original OLS coefficients of around 3.0 and negative 1.8. So OLS said the coefficients should be 3.04, negative 0.01, negative 1.84, and 0.054. And here with Lasso, even with kind of like some of your smallest lambda penalties, it still zeroes out the coefficient for x2 and x4. And again, it has also the side effect of shrinking, because it kind of shrinks all of these penalties, right? Or shrinks all of these coefficients. So instead of 3.04, it's estimating 3.01. And instead of negative 1.84, it's estimating negative 1.78. A little bit of the side effect here. Again, but if you picked another random variable, or not another random variable, another random data set, and you said fit these terms, OLS is going to give you some slightly different values. I would expect Lasso to give you maybe slightly different values for variable 1 and variable 3, but I think variable 2 and variable 4 will be 0 in both of those cases. Okay? If you want, a particular set of values, you can say, all right, when my lambda is equal to 0.2, what are my coefficients? If my lambda is equal to 1, what are my coefficients? And we can see with a larger lambda, it shrinks those coefficients more because, again, the penalty is based on the size of the coefficients directly. So with a lambda equal to 1, we're saying, oh yeah, my coefficients should be a little bit smaller. Okay? How do we decide what lambda do we want to use? Okay, what lambda should we use? Should I use this lambda of 0.2? Should I use a lambda of 1? Which lambda should I use? Okay, well, there is a cross-validation tool. Okay, what cross-validation will do is says, okay, what if we split our data into training and test sets, and we'll do, kind of like k-fold cross-validation. And it's going to say, okay, take your training data, try using a lambda of 1, okay? You'll get these coefficients, right? You'll get a coefficient for x1, basically a 0 for x2, coefficient for x3, and a 0 for x4, okay? All right, so fit the lambda, fit your model using this lambda, and with that, make a prediction on the test. Measure how far you're off, okay? What if you tried a lambda of 0.2? What if you tried a lambda of 0.01? What if you tried a lambda of 0.0001, like a really tiny lambda? Okay, what coefficients would you get? And then now make predictions over here and measure how close you are. And so we can just run this command cv.glmnet and do 5-fold cross-validation, and it says, all right, here's your answer. Okay, and this chart's a little bit hard to read. Oops. Okay, so let me zoom in. Okay, so basically this is log of lambda. So when lambda is equal to, I guess, 3, or 2 point, what is e, 2 point something, 7 something, whatever, right? That's when the log of lambda would equal to 1. And so we're saying, you know, that's when we're basically fitting just the mean and we get terrible performance here, okay? Here, if lambda is equal to 1, your log of lambda is 0. And then here, log of lambda is -1, so I don't know, some, you know, 0.5 or whatever, okay, 0.4. And here it kind of just says, you know, whenever you do cross-validation, we have these error bars because we did 5-fold cross-validation. So we fit a model and we predict it on 20%. We fit a model again and we predict it on 20%. So we end up getting 5 different values for how much error there is. We average all 5 of those things, but in some train test splits we get more error, and some train test splits we get less error. So we get a little bit of error bars here. Okay, and what we're seeing here is, okay, this one right here is where we achieved the minimum, this dotted line over here, and it might be tough to see, but this is where we achieved the minimum amount of cross-validation error. So when we had too small of a lambda, basically no penalty for complexity, our performance actually went down a little bit, because now we have like OLS, you have a coefficient for x1 and x4. They're not very big, but they're not 0, and so now our predictions are a little bit off, okay? And so by having a little bit of a lambda penalty, we're achieving our minimum amount of cross-validation here, around log of lambda being -3. And but if you look at the error bar, this point over here is not significantly different from this error over here. That's what it's saying. If you take into consideration the error bars, this value, which is just a tiny bit higher, and you know, visually on the screen it's a little bit tough to see, but if I line it up down here, okay, if you go horizontally across, you can see this is just a tiny bit higher than the minimum over here, okay? But that difference is not statistically significant, so the general recommendation would be to pick the largest value of lambda that you can that is not significantly different from the minimum cross-validation error achieved. I hope that makes sense. Okay, so you want to pick the largest lambda that is not significantly different from the minimum cross-validation error. Okay, so that's kind of the recommendation. And so after you do cross-validation.glm, you can say, all right, what was the value of lambda that minimized the cross-validation error? And it says, okay, that's 0.05. Okay. And then you can say, okay, what is the largest lambda value that was within 1 standard error of the minimum value? And that one was 0.268, okay? And so if you use a lambda of 0.268, these end up being your coefficients. You end up having a 0 for V2, a 0 for V4, and not quite 3 and 1.8, but 2.76 and -1.57. But apparently that's good enough that we're gonna get still pretty good predictions with our model there. Okay, and so I've kind of written that out on this slide right here. All right, so the benefits of regularization. Okay, why would we want to regularize where we are basically shrinking our coefficients away from OLS? Is that we are going to be reducing the variance at the cost of introducing some bias. Okay, so is it in 100B where you prove that OLS estimates are the BLUE, the best linear unbiased estimators, right? So the BLUE means that in the long run, the unbiased estimators mean that when you use OLS as a method for predicting coefficients, in the long run, they're going to get the coefficient values right, okay? And that if you take the average of, like, if you get one random data set and you fit linear regression to it, and you take your slope, and you get another random data set and you fit linear regression to it, you're going to get a slightly different slope. But if you take the average of all of these slopes after you repeat this many times, the average is going to be the true value. It's unbiased. It's going to converge to the true value. The expected value of the slope estimate is going to be equal to the true coefficient. And best means that of the different unbiased estimators available, this one has the least amount of variance, okay? But again, one issue with ordinary least squares regression is that if you have highly correlated variables, okay, then your coefficients exhibit high variance, right? And that's the issue with VIF, variance inflation factor, is that you have variables that are highly correlated, and so based on just the random sample of data that you get, maybe the true relationship depends on x1 and doesn't relate on x2, but perhaps because of random chance, one day it appears like x2 is the important variable and x1 is not the important variable, okay? And so you get variance in your things, okay? And so what regularization does is it reduces the variance even further, okay? But it comes at the expense of introducing bias. And so now, if you repeat this process of using lasso over and over and over again, the expected value of the coefficients generated by lasso or ridge regression will not be equal to the true coefficients. That's the cost of using lasso or ridge, is that we now have biased estimators. So the coefficients estimated by lasso and ridge will tend to be too small. They're going to tend to underestimate what the true coefficients are, okay? But the benefit is that the variance in these estimates from one random data set to another random data set where you fit the model, the variance is reduced, all right? And that's kind of the bias variance trade-off. Do you want variance in your estimators, or do you want to reduce that? And that might come at the cost of having bias, right? So having less variance is a desirable trait. It means that your model estimates, the coefficients in your model, are less likely to be swayed by the just noise that happens in your kind of random observed data. And so, if you take one random sample and you fit a model, and you take another random sample and you fit a model, and your coefficients are changing a lot from one model to another model, then you're not going to have a ton of confidence in your coefficient estimates. You might feel like, oh, did I get a coefficient that's too big, a coefficient that's too small? It's hard for you to really know, okay? On the other hand, if you take one random data set and you get a coefficient, and you take another random data set, and your coefficient from that thing is almost exactly the same as the one from your first data set, then you can feel pretty confident. You can feel like, okay, I've got good coefficient estimates, right? Because we're very consistent, right? That's always kind of encouraging, is that whenever you're trying out an experiment, if you're getting like the same results every single time, you can feel good about what's happening, versus every time you try out the same thing, if you're getting like wildly different results, you go, oh man, I'm not very good, right? It's like, do people go bowling anymore? It's like, if you suck at bowling, every time you throw the ball, you have no idea where it's gonna go, right? Whereas like the good player can consistently get it to do the same thing over and over again. So lower variance is a desirable trait here, okay? So here I'm gonna just show you a little bit, like simulate a bunch of random things and show you what lasso does and what ridge regression does on how it lowers the variance, but introduces bias. And I think you have basically similar charts that are going to appear in your homework as well. But this is going to try to illustrate this bias variance trade-off, okay? So again, here I'm generating a population. There's correlation between x1 and x3. And the true relationship between the y and the x variables is that we do 3 times x1 and negative 1.8 times x3, okay? And there's no actual correlation between, or no relationship between y and x2 or y and x4, okay? And what I'm going to do is, this is my true relationship, but I'm going to generate random noise and we'll get some observations, okay? So I'm going to generate random noise. We're going to add that random noise to the true values of y, and then we're going to try fitting ordinary least squares regression. We're going to fit lasso. We're going to fit ridge regression, okay? And then for each of these things, we're going to use cross-validation to select the model that kind of has the minimum lambda there. And we're going to store all of the coefficients here. So this is kind of the code that I run. So random noise gets added. We're going to try to predict y based on the X matrix, and we'll get the OLS coefficients. We'll get the coefficients for lasso, coefficients for ridge. Okay, so we look at OLS. Remember, the true coefficient in the true relationship is 3.0. And OLS, we look, and the mean is indeed 3.0. Okay, so this shows us that it is unbiased. Okay, we look at lasso, and the mean is like 2.65, 2.7, so not quite the true value. And then ridge regression is like way different. The mean is like 2.2. Okay, one thing I do want you to note, though, okay, is that what is the variance? The variance on the OLS is sometimes it gets as low as 2.5 or sometimes as high as 3.5. I would say that covers kind of your middle 95%, going from 2.5 to 3.5. If we wanted to cover like the middle 95% for lasso, we'd probably go from around 2.4 to 3.0, maybe we can be generous and be 2.3 to 3.1, okay? And so the amount of variance in the lasso coefficient estimates is less, right? Where if we go, say, from 2.4 to 3.0, that's a distance of around 0.6, versus here we're going from 2.5 to 3.5, we're getting a distance of around 1, okay? As far as that kind of middle 95, 90-something percentage, okay? Ridge regression, not super great. We're getting like 1.9 to 2.7, okay? So 0.8 of a difference there, okay? But we can see that's the amount of variance in these estimates is reduced, especially for lasso. Maybe not as much for ridge regression over here, okay? But we do see the bias, right? The true value is 3, and OLS is centered around the true value of 3. Lasso is centered around 2.7, and ridge is centered around maybe 2.2, okay? And that's what we see. So the variance, here I measured the actual variance for the OLS of 0.06. The variance is 0.06, whereas for lasso, the variance of the coefficients is 0.03. So the mean of OLS is right around 3, 2.997, and the variance of those estimates is 0.06. For lasso, the mean is 2.68, biased, but variance is less, 0.033. For ridge, there's a lot more bias. The mean is 2.26, but the variance is reduced as well, 0.04, okay, 0.045. Okay, here we have, let's look at the coefficients for x2, okay? So for x2, remember the true relationship is that y is not related to x2. The true coefficient should be 0, okay? True coefficient should be 0. And for OLS, most of the time we get something around 0, but sometimes we get values as low as like -1, values as high as +0.5, okay? So that's one of the issues with the OLS, is that you've got kind of this wide variance of these things. Overall, the average is 0 though, okay? For lasso, it like consistently and successfully shrinks the coefficient down to pretty much 0 almost every single time, okay? Yes, sometimes we get a coefficient that's a little bit higher, 0.1, 0.2, 0.3, okay? Something around there. Okay, ridge regression, it introduces a lot of bias. It's centered around 0.5, but the amount of variance is going to be small here. Okay, so if we take a look at OLS, the average of all of our coefficients is pretty close to 0, negative 0.02. Okay, but the variance is 0.087, which is comparatively high when we look at LASSO and when we look at Ridge. So if you look at LASSO, the average of all of these things is pretty close to 0, 0.022. There are some occasions where the shrinkage didn't push it all the way down to 0. But the variance here is 0.0087, all right? So 1/10, right? So OLS, we had 0.087. LASSO, the variance is a lot less, 0.0087, okay? Ridge regression, the mean is pretty high, 0.49, okay? But the variance is also reduced 0.04 compared to 0.087, okay? And so one thing about ridge regression is, again, with ridge regression, it tends to push the coefficients towards each other. So remember, the true value for x1 was 3, and the true value for x2 was 0, but ridge regression tries to kind of push these things towards each other because it prefers where, with the circles, it prefers where W1 is equal to W2, right? And so, so in that case, it's going to try to push up the coefficient for x2, which really should be 0. It pushes it away from 0, and it pushes that true value of 3, towards each other, 2 point something. Okay, and if we looked at the x3 and x4 coefficients, we would see a similar thing. Okay, so this all kind of comes down to the bias variance trade-off, and if you do some calculations symbolically and stuff, the expected prediction error is equal to the bias squared plus the variance plus the irreducible error of just in the relationship there. Okay, so error is the true relationship, expected value of the true relationship plus random error minus any fitted value, so the actual values minus the fitted values. Bias is the expected difference between our predicted value and what the actual values for the new values of x, what the true values are. Variance is the variance of the predicted values, and sigma is the standard deviation of the noise in kind of generating that data there. Okay, I'm going to just show you some spaghetti lines here. This here represents the true relationship. This solid red line represents the true relationship. Before I forget, let me give you your second view quiz answer. Letter C. Today there's only 3 answers, so the second one is the letter C. Letter C. Okay, and I'll give you your third answer. So this represents the true relationship, okay? And what I have here is I'm going to generate some random values. Oh, you can't see it. Okay, you cannot see it on this projection, but there are dots. They're really hard to see. They're like lime green here. There's like dots. Okay. I'm sorry. Okay. The projection makes it impossible to see. But there are dots generated around this dotted red line. Okay. And if you take those dots and you fit a straight line to the random dots generated around the red line, this straight line will be the line that best fits the random dots. Okay? Okay, here you can actually see the dots. Okay? So here I generated another set of random dots around the curved line. So remember, the true relationship is the curved line. Okay? And I've generated some new random data around the curved line. And I said fit a straight line to these dots. And this is the line that gets fit. Okay, and I used a different color, and I don't know if you can see, but there are also different dots around the curved line. And I said fit a straight line to those different dots. And this straight line is the line that gets fit, okay? And so if you plot those 3 straight lines, they all end up being just ever so slightly different, okay? Because the random data around the true relationship, the random data was different, therefore the regression line that got fit is a little bit different, right? They're similar, but the intercept is a little bit different, the slope is a little bit different. Okay, so we're saying this is what represents the variance in our estimates. Okay. On the other hand, I've generated some random dots, okay, around the dotted red line, and I said fit a line that fits those dots, and this is the line, because and so there actually is a dot right here, and it's trying to fit that. Okay. And then here are, again, you can see the dots here, different random dots. And I said fit a line to those different random dots. And then here's another one where there's different random dots, and I said fit a line to those different random dots, and so we get a squiggle line. Okay? And so if we plot the three different lines that were fit, we see a lot of kind of squiggling here. Okay? And so this has a high variance between the different lines, and the lines differ very much from one random data set to another random data set. Okay, high variance. And to get to the idea of bias, I'm going to do this like 100 times. And so here, this represents 3 different random data sets, and I fit 3 different lines to it, and we can see these 3 lines are very different from one another. Okay, and this also is 3 different random data sets, and I fit 3 lines, and these 3 lines are slightly different from each other. And to repeat this, I'm going to do this 100 times. Okay, and I'm going to plot this out. So what you see here is the true relationship is the curved line in black. And after fitting sampling 100 random data sets, I said, okay, fit a straight line to that random data. And so this, it's hard to see, but there's 100 different lines drawn here. And then these white dots represent what is the average prediction made by all 100 of those dots when x is equal to 0. What is the average prediction made for all 100 of those dots when x is equal to 0.2? What is the average prediction made for all 100 of those lines when x is equal to 0.4? That's what these white dots represent. Okay? So what we can see is that these white dots do not line up with the true relationship quite well. Okay? So that represents the bias between the best we can expect our model to perform and the true relationship is not very close. Right? So in the long run, how good can we expect our model to perform? That's going to be these white dots. Again, you're dealing with one random data set. So you might get the line up here, you might get the line down here, you might get the line that's too steep, you might get the line that's too shallow. But in the long run, overall, if you fit a straight line, this is kind of the white dots represent kind of the best. But even in the best case, these white dots do not line up with the true relationship shown in this black line. So that's high bias. Okay. However, how much do these lines differ from each other? They don't differ very, very much, right? The most extreme line is like the line that's way up here, and the most extreme line over here is the line that's down here. And there's not a huge difference between like the extreme highest and the extreme lowest. So not a whole lot of variance. So we have high bias, low variance when we fit straight lines. And that's what we would consider underfitting. Underfitting is kind of high bias. The white dots do not fit the true relationship very well. Okay. However, the different colored lines do not vary drastically from each other. Low variance. This mess over here is a model that overfits. Okay. So you have this huge kind of rainbow spaghetti going on here. All right. And again, if you take, so there's supposedly 100 lines, I don't know. Okay, if you take all 100 lines and you say, all right, what is your prediction when x is equal to 0.4? And we take the average of all of the predictions made by all of these different lines, we get this average right here, okay? And then we say, okay, when x is 0.5, what is your prediction? We get this average right here, this white dot. And we can see the average of all of these different spaghetti lines ends up pretty close to the true relationship. It's not exactly, like if you look closely, like right here, you can see this white dot is a little bit below the true line at 0.5, and this white dot is a little bit above the true line at 0.5, so it's not perfect. But overall, I would say these white dots line up along the black line, the true relationship, pretty well. Okay, I would say the average of those of these dots is pretty close to the true relationship. So we would say there's low bias here. In the long run, we can expect this model to do a good job of fitting the true relationship. But in real life, you don't ever actually get the true, like the optimum, right? You only get one of these random samples, okay? And so you don't know, did you get the crazy spaghetti line that goes, way up here, or do you get the crazy spaghetti line that goes way down here? You don't really know, and so you have a huge amount of variance from one spaghetti line to another spaghetti line here, okay? And so the white dots do fit the true relationship well. We have low bias there. But on the other hand, those colored lines, the squiggly colored lines, do vary very much, drastically from each other. And so we have high variance, right? So the optimum is we want to get something somewhere in between. We want to get something where we have low bias and low variance. We want something between these two extremes where the average of these white dots is pretty close to the black line, and how much variance is there from one kind of spaghetti strand to another? Not as much, right? And so this is something in between where we're not kind of getting, right? And so this is kind of the goal for machine learning, is you have these different options available. Do I fit a whole bunch of variables? Do I fit a whole bunch of parameters that allows me to have this very flexible model, but perhaps too much flexibility, and we get high variance even in the long run if we have low bias, okay? Or do we rather have something that doesn't have as much flexibility, but then its predictive performance isn't as good, okay? And that would be kind of your low variance, high bias. And what you want to do is find the right values to get something in between where you have not too much variance, not too much bias. Okay, that's kind of what we want. All right, so we're going to take a jump, and now we're going to talk about, I'm going to introduce neural networks here, okay? And neural networks are just kind of fun. They're kind of cool. And we use gradient descent when we train a neural network. So it's very applicable of what we are doing with gradient descent here. Okay, a lot of my notes and lecture slides are based off of the Welch Labs Neural Networks Demystified playlist. So these are both channels that I highly recommend, Welch Labs and 3 Blue 1 Brown. I've already mentioned 3 Blue 1 Brown for their series on linear algebra, and really there's just like a whole bunch of really great math stuff in there, and Welch Labs also has some great math stuff in there too. But anyway, these are different playlists. Highly recommend that you watch both of those playlists. So neural networks have technically been around for like decades, I guess since like the 1970s and 1980s, and but they've gained a lot of popularity more recently because we have been able to make really complicated neural networks because we have this computational power, right? So we have these very powerful computers that are able to do like millions or millions of multiplications or billions of multiplication operations in within a second, and which is necessary to power a neural network. And these neural networks are basically used to power basically all AI stuff these days. Okay, so all AI stuff, your ChatGPT and all of your image recognition stuff is all basically powered by a neural network. There's been like just within your phone, the amount of technological leaps that have happened within the last decade are truly astounding, right? Now you take a picture and your phone is able to recognize what you took a picture of. And later on, when you say, hey, show me all of the pictures of this person, it's able to find them all, right? That's like amazing, right? Because if you gave a human this task and you said, all right, find all of the pictures of my friend or something, it's like, oh, I don't even know, like, is this your friend or is this like, sometimes you look at like old photos and you're like, is this me or is this like my brother or something? You know, it's tough, and the computer is able to like do this kind of stuff, right? It's really, really amazing. In our class, we're not going to do the cool stuff, okay? We're just going to look at the most simple neural network, okay? Just a very, very, very simple kind of neural network. And we still do something kind of cool with it. I think it's still really neat. We use gradient descent, but we're just going to look at the simplest of the neural networks. But really, the advanced neural networks that we're looking at that power all of this stuff are really just an extension, right? It's just an extension. Here we have like one hidden layer with this many nodes, and the powerful neural networks just basically have more nodes and more hidden layers, like millions more, but it's just the same thing, but just more, right? It's kind of like with linear regression. Once you learn multiple linear regression, you know, what's the difference between a model with 2 predictors and a model with 200 predictors? There's not that much of a difference. It's just the complicated one has more. And that's basically what the AI models are. They're just neural networks that have more, all right? And so when you have hundreds of these nodes and stuff, hundreds of these layers, we call that a deep neural network or deep learning and things like that, okay? At its core, like the term neural network just sounds cool, but really it's just a function. It's just a function. And what does a function do? It takes an input, does math, produces an output, okay? That's all it is, okay? So just think of a neural network as a function. Takes an input, does some math, produces an output, okay? And it's just, well, how is the math done? The inspiration is kind of the brain. I guess that's the neural part of it. And so within your brain, you've got these neurons, and each of these neurons have these, axons and dendrites and synapses, and they connect to these things. I don't know, use cog-sci majors here, okay? And basically, your neuron, based on some stimulation, like your eyes see something, or you feel something on your skin, or you hear something, right? Signals come in, these are electric signals, and based on what happens to those electric signals, a neuron might activate, and if it activates, it then sends a pulse to other neurons, and this all happens billions of times in a second, and then at some point, the neurons that correspond to speech work, right? And it's there's a little bit of this existential thing that you think about. You're like, oh, am I just a bunch of electrical signals going on? and these thoughts that I have in my consciousness, I feel like it's me and it's real, but really, am I just do I actually have any choice? Is it just the electrical signals and I have no kind of actual control over this, right? It's like if you hit the on switch on your computer, it's just going to do what it does, and I don't know, right? But anyway, not to worry about that. So basically, within your brain, depending on the signals, the electrical signals that come in, that neuron might light up, or a different neuron might not, and that's going to determine what kind of reaction and what kind of output we have. Okay. And similarly, a neural network that we create on the computer, okay, is just a bunch of these nodes where we have these numbers, these input values coming in. Depending on the value that comes in, that node and the activation function, it will send a new value to kind of the other nodes. So we're going to look at this very simple example. We have 2 predictors in our X matrix, represented with these 2 columns, and we have one output in our Y matrix, okay, one column of outputs. And this is coming straight from the Welch Labs video. This is the example he used, and he said we're going to do hours of sleep and hours spent studying, and what is our exam score, okay? And so I guess when we had 3 hours of sleep and 5 hours of study, we scored a 75, okay? 5 hours of sleep and 1 hour of study, we got 82. 10 hours of sleep, 2 hours of study, 93 or something like that, okay? So, I mean, this is just a very silly data set. We only have 3 observations here, but that's okay. We have 2 input variables and one column of outputs. And basically, all of our neural networks, we start off with the input layer, and we have 1 node for each variable in our input. So in our case, we have 2 columns, and so within our input layer, we are going to have 2 nodes. 1 node for each column, 1 node for each variable, okay? The output, we have 1 node in the output, which is our exam score, okay? And so the output layer has only 1 node. In future examples, we might have like multiple outputs in the multiple nodes in the output layer if you have if you're trying to predict a category or something like that. Okay, and then here we're just going to have 1 hidden layer. For our simple example, we will have 1 hidden layer, and this hidden layer will have 3 nodes. And this is just an arbitrary choice, but I'm just picking 3 nodes just to keep it very, very, very simple for this beginning example, right? And so we go from the input layer to our hidden layer to our output layer, and that's about as simple as a neural network as we can get. And so this is our diagram here. I've got 2 nodes in the input layer, 3 nodes in the hidden layer, 1 node in the output layer, and each node in the input layer is connected to each node in the hidden layer. So this node connects to all 3 layers in the hidden layer. This node also connects to all 3 layers in the hidden layer. Okay, and then every node in the hidden layer connects to every node in the output layer. So there's only 1 node in the output layer. So this node connects there, that node connects there, and that node connects there. So we have basically 6 arrows over here and 3 arrows over here. And effectively, training our neural network is figuring out how much, like multiplication, what values do we put on each of these arrows. Okay, so a deep learning side note, I already mentioned this. Basically, all of the things that power AI and stuff is a lot of this is like all just neural networks, and it's basically the same thing that we're doing here, okay? Except instead of 3 nodes in the hidden layer, just imagine like 10,000 nodes, okay? And instead of 1 hidden layer, imagine like 1,000 hidden layers, okay? And so you might have millions or multiple millions of nodes, okay, and you've got thousands within each layer, thousands of layers, okay, and you might have other operations where it's like you're going to combine certain nodes and stuff like that, and we call those like convolution layers and things like that. But basically, it's the same kind of idea, same structure. Just imagine having more nodes and more layers, and once you start hitting over 100 layers, and then that starts falling under deep learning, okay? It's like a stack of these things. And basically, I guess this is almost a decade ago. I remember this being huge news when the deep convolutional neural network surpassed human error rate for labeling images. So there was we were training our neural networks based on this huge image data set. This was like, okay, here's a picture, and we asked, okay, what is this a picture of? And it would be like, this is a picture of a boat. This is a picture of a bicycle. This is a picture of a house. This is a picture of, the dogs were hard because they had specific breeds. This is a picture of a Labrador. This is a picture of a poodle. This is a picture of a Shih Tzu or something like that. So that was pretty tough. And so humans would make mistakes. They would probably get like 95% of these things correct. And for the longest time, the computers and the neural networks just sucked. They would only get like 30% accuracy, 40% accuracy or something. And then in 2015, it was like 96% accurate, beat the humans. And then ever since after that, it's now like 99.8% accuracy. And the ones that make a mistake are like, oh yeah, this is just a bad picture or something like that. Okay, so now like humans, there's no catching up to this, right? It's kind of like it was a big deal when the computer first beat the human at chess, and now there's just no catching up. Like no human will ever come even close to a computer's chess playing ability. And so, I don't know what's going to happen, right? And now AI is like generating artwork. We always thought like art and music and these were like the pinnacles of human creativity. And now it's like, give me a picture of, the president riding a bear and something like that. And the computer generates this, right? And you're like, oh, this is pretty good. But, anyway, that's kind of interesting here. All right. One note thing is that neural networks, they are great at what they do, which is make predictions, produce outputs. Okay. Neural networks, we cannot interpret them, right? Linear regression, you get a coefficient and you can say like when x goes up by 1, my y goes up by this parameter, right? That was like a basic interpretation of the slope. And so linear regression, easy to understand, easy to interpret. Neural networks, we have no idea what's happening, okay? And that's kind of the problem is you ask, like, there's all of this scrutiny now with like, who's controlling what shows up in my feed, right? Like TikTok shows you this video and then it shows you this video and it's like, are we promoting like conspiracy videos or things like that, right? On YouTube, you click something and then like all of these other things start showing up and you're like, watch next. And you're like, who's controlling all of this? And it's not like you can open up the thing and be like, oh, okay, this is the node that's working funny and we need to fix this, okay? Because now we have like a million nodes in here and nobody has any idea what any of these nodes are doing, okay? It's kind of like if we did brain surgery and we opened up your brain and we said, hey, what is this neuron doing? We like zoom in with a microscope. What is this neuron doing? No one's going to be able to say, oh, this is the neuron that's in charge of this, okay? We have no idea. We can say this part of the brain generally lights up when they're like looking at something exciting, and so we think this is something, and we might be able to do that, but we really have no idea what one particular neuron or node in your brain is doing. And similarly, you say, hey, what does this coefficient mean? We have no idea, right? And it's just, we're only just measuring our performance by saying like, okay, I want this, and is it giving me that? It is. And right now, all of these YouTube, TikTok, Facebook, Instagram feeds, they're all just kind of like, is the person staying logged into the device? Yes, we're doing great, okay? And that's kind of the metric. Is that a good thing or bad? I don't know, whatever, okay. But we'll talk about our neural network here. So we just have no idea what's happening, okay? So here's our network. We've got 2 nodes here, 3 nodes here. We've got 6 arrows going from here to here, 3 arrows going from here to here. So we have 6 connections between the input layer and hidden layer, 3 connections from the hidden layer to the output layer. Each of these connections, each of those arrows, we are going to put a weight. We're going to put some kind of number, like 3 or 0.1 or whatever, okay? And that number is going to tell us how important the connection from this node to this node is, okay? But again, we don't really know what that connection means because we don't really know what the nodes actually represent. But we're just gonna say, all right, these are the parameters I can play around with. So linear regression, you had an intercept and different like slope values. Here we have these different weight values that we tie to these connections, these arrows here. And so now training our model is not figuring out the intercept and the slope, but training our model is figuring out what numbers to put on these arrows, what numbers should go on our weights. That's what training a neural network means. It's just figuring out what all of these weights should be. And so when you have a really complicated model with millions of nodes, you might have on the orders of hundreds of millions, if not billions of connections, and training your network there is all about figuring out what weights, what numbers to attach to those arrows. So we are going to label, and I hope you can read this, okay? We are going to label each of these weights. So the weight going from layer 1, from node 1 in the input layer to node 1 in the hidden layer is weight 1, 1, W11, okay? The weight going from node 1 to node 2 is weight 1, 2, and the weight going from node 1 to node 3 is weight 1, 3. Okay? Going from node 2 to node 1 is weight 2, 1. Going from node 2 to node 2 is weight 2, 2. And going from node 2 to node 3 is weight 2, 3. All of these have a superscript of 1 indicating that they belong to the first weight matrix. In the second weight matrix, all of these will have a superscript of 2 to indicate they belong in the second weight matrix, and we have a similar notation. It is impossible to read on the projection here, but the weight going from node 1, there's only one node in the output layer, so node 1 to node 1 is weight 1, 1, node 2 to node 1 is weight 2, 1, and node 3 to node 1 is weight 3, 1, and they are arranged here as well. So the 6 weights in the first weight matrix are arranged in this matrix, 2 rows and 3 columns. We have W11 going from node 1 to node 1, W12 going from node 1 to node 2, W13 going from node 1 to node 3. Okay, W21 node 2 to node 1, node 2 to node 2, and node 2 to node 3. So this is the notation that we use, okay? So W1 has 2 rows, 1 row for each node in the input layer, and it has 3 columns, 1 node for each, 1 column for each node in the hidden layer. And then W2, the second weight matrix, has 3 rows, 1 column. We have 3 nodes in the hidden layer, and we have 1 node in the output layer, so we have 3 and a 1, okay? And again, this is for our simple network. We have a total of 9 of these things. Deep learning, you just have like 1,000 by 1,000, okay, for one weight matrix, and you'll have like 1,000 of these weight matrices, right? So you just have a whole bunch of these things. So when you have input values x, we will take our input values x and multiply it by our first weight matrix. So we're going to do x, which has n observations in 2 columns, right? So we have n observations, 2 columns, 1 column for hours of sleep, a column for hours of study. And we're going to multiply it by our first weight matrix. First weight matrix has 2 rows and 3 columns. So the output will be an n by 3 matrix, and we're going to call this thing Z2. Z2. While I'm here, let me give you your third view quiz answer. Third view quiz answer is the letter E. E as an elephant. E as an elephant is our third view quiz answer. Okay, so so when you do this, the first value is x11 times w11 plus x12 times w21, right? And then first row, second column is, basically this first row multiplied by the values in the second column added together. And then in the third column, you take, this first row, multiply it by the third column of values, and that goes into this third row, okay? And then we do this, and so we're going to get a total of n rows corresponding to the number of rows in X, and we're going to get a total of 3 columns here. All right, so this is our huge matrix, okay? And in the lecture notes, these are all color coordinated. You can't hardly see the colors on this slide. And I typeset this in LaTeX, and I want you to appreciate the amount of work it was to color coordinate these symbols with subscripts and superscript in LaTeX in a big matrix there. Okay. So anyway, you get this n by 3 matrix Z, and what we will do is we have an activation function. Basically, we just take a function and we apply it to each value in this matrix. Okay, so we have n by 3 values. We are going to just apply a function to every single one of these values. So the result is another matrix of the exact same dimensions, because we haven't changed any of the dimensions here. It's just, if the top left number is a 1 and we apply a function, let's say the function is a square root, then the top left number is going to be square root of 1, or I guess 1, right? If the next number is a 4, we do the square root and we get a 2 or something, right? So we're just applying a function to every single value in this Z matrix, and we get another matrix, same dimensions, and we're going to call that A, as in like the values after running the activation function. after the activation function. Okay, our activation function, we are going to use the sigmoid function, also known as the logistic function. And basically, we will take values going from negative infinity to positive infinity, and they get squished on the range 0 to 1. Okay, this is basically what your logistic or sigmoid function looks like. So as x goes to negative infinity, you approach 0. As x goes to positive infinity, it approaches positive 1. Okay. The sigmoid activation function was kind of the primary activation function used for a long time. It has now fallen out of favor, and I would say modern neural networks today do not use this sigmoid activation function. Okay. Most of the neural networks today use what's called the rectified linear unit, ReLU function. There is a whole bunch of different activation functions you could look up on Wikipedia, and they have little different pictures of what these activation functions could look like. Okay. But we'll go ahead and continue just using this sigmoid activation function. It's the same function that's used in the video series. It's differentiable and, historical popularity. Okay. So anyway, this is what we have. All of our nodes are labeled, and we're going to try to figure this out. So we've taken from our input matrix X, we've multiplied it by our first weight matrix W, and that results in the values Z in our hidden layer. And then we run our activation function. So I don't have A's written here, but we run the activation function. So we have a matrix, n by 3 matrix of activated values. This is after we apply that activation function here. And what am I going to do next? I'm going to multiply it by our next weight matrix, which is our W2 weight matrix. Our W2 weight matrix has 3 rows and 1 column. And so if we multiply our n by 3 matrix by a 3 by 1 matrix, the result is an n by 1 matrix, right? This looks kind of complicated, but this is just one single value. It's A11 times W11, A12 times W21, A13 times W31, okay? And you add them all together. So they reduce down to a single value, right? You're doing 3 multiplication operations, but then you just add them together. So you get just one value. So this is just one column of values. And that is, that's going to give our next matrix, Z. We call this Z3. Z3, or I guess our third layer, values in our third layer. And then finally, we will run the activation function again to these values in Z, Z3, and this will give us our predicted values Y hat. Okay. So in summary, these are the operations we do. We have our input matrix X, n rows by 2 columns. We multiply it by our first weight matrix, 2 by 3, and that gives us our Z matrix for the second layer, which has dimensions n by 3. We apply the function f, our activation function f, to the values in Z. These give us the values A2, our activated values in our second layer. We take the activated values in our second layer and we multiply it by our second weight matrix. And this gives me my Z values in the third layer. And finally, I apply the activation function to the Z values in my third layer, and that gives me my predicted Y hat values. So Y hat can be simplified. I don't know if simplified is the right word, but can be just made into one thing, which is apply X times W1, apply the activation function, take those results, multiply by W2, and apply the activation function out there, right? Anytime you see like functions with nested functions, always start on the inside and work your way outwards. So X times W1, apply function, multiply that by W2, apply the function. That is Y hat. Okay, and that is forward feed. Okay, that takes our inputs and shows us how we get to our outputs. Another thing is that you can also have bias terms. Bias terms basically add a constant to each node. So this has the effect of basically sliding the values up and down, okay? And that just gives us another kind of parameter to that we have to play around with, okay? So we just add a constant before applying the activation function. So here I have put these B terms, I guess my first set of biases, B1, and I've got 3 nodes, so each node has their own bias term, B1, B2, and B3. And then in the output layer, we also have a bias term. There's only 1 node, so we've got just a B1 there. So we have 1 bias term for each node, and so our hidden matrix, matrix of bias values for the hidden layer, and we're going to call this bias matrix B1, is 3 by 1, okay? 3 rows, 1 column of values. For our dimensionality to work, we have to multiply the bias matrix by a matrix of 1s. So remember, the values in our hidden layer is basically x times W1. So this is an n by 3 matrix, right? N by 2 times a 2 by 3. We have an n by 3 matrix. This is technically our Z2 values. And we want to be able to add some constants here, okay? But right now, our B1 is basically just 3 values here, okay? And I can transpose it, and so I have 1 row of 3 values, but I can't combine that with XW unless I duplicate it n times, right? So I have n rows and 3 columns, and B transpose is just 1 row and 3 columns. What I have to do is I have to duplicate that across all of the values. So I'm going to multiply it by a matrix or a vector of 1s called J. And so we're going to have n rows of just 1, and that's going to be J. And that will form an n by 3, and then I can add XW1 plus JB1 transpose, and that will form our Z2 matrix, n rows by 3 columns. So the illustration looks kind of like this, right? So X times W1, n rows, 2 columns, by 2 rows, 3 columns will produce n rows and 3 columns, okay? And then here I've got n rows, 1 column multiplied by 1 row, 3 columns. And this will also produce an n by 3 matrix, right? This column of 1s multiplied by this row vector or row matrix of 3 values will also produce n by 3. And so now I have an n by 3 plus an n by 3, and I can combine those. And so here's all of the things. I got x1, 1 times w1, 1 plus x1, 2 times w2, 1 plus b1. And the b1 gets added to all the values in this column. b2, the same b2 value will get added to all of this column, and then the same b3 value gets added to all of the values in this column. So that fills out our matrix. Same thing that goes on with our second set of biases. In this case, there's just 1. Okay, and so here I have A times W2. Okay, and so this will produce an n by 1 column matrix. And here I have n rows, n by 1 here, and I'm going to multiply by b1. Here I have b2 transpose. This is a scalar, so it feels silly to transpose. But if we had, to generalize, if we had 4 nodes in the output layer, then b2 would be 4 by 1, and we would need to transpose it, so it's a 1 by 4. So I'm going to keep the transpose here. And so, the same b1 value gets added to all of the values in this to give us our z3 values. Okay, and then we would apply the activation function. So in our case, with bias terms, we take our x matrix, multiply it by our first weight matrix, plus j times our b1 matrix. That gives us z2. We apply our activation function to z2, and that gives us our a2 matrix. Then we take our a2 matrix, multiply it by w, and add j times b2 transpose, right? That gives us z3, and we apply the activation function there. So to kind of combine it all in one, we have xw1 plus jb1 transpose inside the function, activation function, multiply that result by w2, add jb2 transpose, and throw that inside the activation function. and that gives us our predicted values. Okay. It's kind of a lot, but this is a forward feed for a neural network. Okay, so this is how we go from our inputs and whatever weights and bias terms we have to get to our output. Okay, and that's the forward feed part. And then next week, we will take a look and say, all right, how do we train our neural network? And so to train our neural network, we are going to have this objective function, and the objective function is the same objective function that we use in linear regression. We take a look at the values we are predicting and the actual values, and we want to shrink the sum of squared residuals, or the mean squared error there. Okay, so we're going to say, okay, what are the values that I'm predicting, y hat? What are the actual values? We're going to square that difference and sum them up. Okay, so basically in matrix form, that's y minus y hat transpose times y minus y hat. It's just, how did we arrive at y hat? Y hat is the result of this, or the result of this function. Okay, and so now the trick is, okay, how do I pick the W1, the values in my W1 matrix, or how do I pick the values in my W2 matrix that will give me the y hats that are as close as possible to the y? Because that's our goal, is to shrink the difference between y and our predicted values y hat. So how do I pick the W1s and the W2s, or the betas and the beta, not the b's, the bias values, and our B1 or B2 matrix and things like that? Okay, and to do that, we're gonna calculate the gradient, and we will do gradient descent, because calculating gradient and setting it equal to 0 and solving is not gonna be possible, okay? But we have gradient descent, which is a tool that says if you got the gradient, you can just keep going downhill. And we'll take that and we'll write it downhill, and that will get us to some local minimum or some kind of minimum that optimizes our performance. So that's where we're headed next week. All right, and that is it. That's it for today's lecture. Have a great rest of your week. Good luck with your homework, and we will see you on Monday.